The gravitational field of black holes is so great that they can deflect, trap, and pull in light. So we can't really see them directly, but we can see the things around them that emit light. We could even see ourselves. This light that comes back to us is known as boomerang photons. If we were to flash light next to a black hole, not all of the light rays would come back to us. Here, we calculate the ones that do. Photons travel along null geodesics. Bound to the planes of spherically symmetric black holes, we can numerically integrate them to find photon orbits. Conveniently, we need only to look at their impact parameters. Photons with the critical get captured in the photon circle, and photons with Bn complete n revolutions around the black hole before coming back. We inspect the turning points of impact parameters greater than and less than Bn. Finding the impact parameters of boomerangs is like an eigenvalue problem that can be solved with a bisection method. I shall refer to the discrete set of impact parameters as the spectrum. In this thesis, I study how the boomerang spectrum depends on possible black hole parameters like charge, cosmological constant, and spacetime dimension. The farther you get from a Schwarzschild black hole, the critical stays the same, and the spectrum becomes wider, whereas the spectrum expands as the universe inflates. For charged black holes, the spectrum overall shrinks and becomes narrower with greater charge. And when you go to higher dimensions, the spectrum shrinks and narrows so dramatically that it's harder to tell even between B1 and the critical. If we can get closer to a black hole, we can do more things in the future with being able to calculate just B1, like a halo drive, and perhaps make fuel-free interstellar travel possible.